All right, good afternoon, everybody, and welcome to Intro to Space Navigation, Spring 2025, Lecture 9. I think I made a mistake at the beginning of the last recording and said Lecture 7. That was actually Lecture 8. Sorry about that. So today's going to be Lecture 9, and I'm going to go ahead and share my screen here. So maybe you all remember there was a course map that I introduced on the first day of class, which looked like this. And it's kind of got a lot going on, but I wanted to be able to point to a single image and have it immediately make sense how today's lecture fits into the overall plan of what we're trying to learn. And so we've basically finished the orbital mechanics section. So first we talked about reference frames, ICRF frame, Earth frame, Moon frame, spacecraft body frame, the relationships between frames, means we need to know about attitude representation. We learned, the basic orbital mechanics. We learned how to propagate an orbit. We learned Kepler's equation. We learned the orbit elements. We learned how to go from a state to an orbit and back again. Then we learned about orbit determination. So if you have a partial state, like a bunch of positions over time, you can deduce the rest of your state, like the velocity at one of those times. And if you have your full state, you're good to go. You've solved orbit determination. So we talked about those things. Today's lecture doesn't really fit too neatly into any of these categories. It's kind of a awkward middle child that wherever I put it, it's going to feel kind of shoehorned in. But today's lecture is on what's called matrix vector calculus, which is a mathematical technique that we're going to use over and over again in this course. So I guess you could say that we're moving from orbital mechanics to estimation theory and then in parentheses math. So this is going to be a math lecture. And then moving forward, the next couple of lectures are all going to be estimation theory lectures. So answering questions like, how can I solve for these unknowns given these measurements? And then what if we need to weight the measurements based on how much we trust them? And then how do we quantify the uncertainty that comes out of that? And things like covariance analysis, that all comes in estimation theory. So that's our next major unit. And today is kind of a bridge between those. So we're just going to talk about matrix vector calculus. And then after that, I believe we move into triangulation and trilateration. But I don't have my whole course schedule in front of me right now. But that is the plan. So let's talk about matrix vector calculus. Here, stand by. There we go. So for people who didn't think that calculus was complicated enough, calculus is on scalars. We're going to be talking about calculus on vectors and matrices. So we're going to be able to answer questions like, what is the derivative of a matrix? Oops, stray mark, sorry. Or, what is the derivative of a scalar, WRT, with respect to a vector? Or how do we compute derivatives of vector and matrix equations? So the tool we're going to use is matrix vector calculus. And this is a tool we will use over and over again in this course. And this will come up on at least one homework assignment I think you need to be able to take. So we're going to talk about taking partial derivatives of vector equations, which is absolutely necessary the later we go into this class. Sorry, I have a tendency to start talking before I finished writing in this course. So actually, last year, when I taught this class, I gave a lecture on matrix vector calculus, and I regard it as my worst lecture that semester. I think it was the one where I understood the material the least, which meant that I kind of just read off my notes, and I don't know if I really imparted any wisdom or understanding into the students. But then over the course of the semester, we kept using matrix vector calculus in examples, in derivations, and homework assignments. And so I've torn down my old lecture notes and started over completely from scratch. And I want to teach this topic in terms of how we will use it later in this course. That's kind of the goal. So I got rid of some of the more arcane theory, and this is going to be more practical applications of matrix vector calculus. So we're going to do a bunch of examples. And later in this class, probably at least 2 or 3 times in this class, I will say, we'll come to some point and I'll go, oh, we actually already did this back in the matrix vector calculus lecture. So hopefully this helps. So let's start simple and build up. This is going to be a very example heavy class. All right. Let there be some function f of x1 to xn that takes in a vector of n inputs and produces one output, or one scalar output. So in mathematical notation, you might see this, especially those of you that are on the grad school journey, you might see this written something like the function of the vector x maps real numbers to the power n onto real numbers. You might say something like that. This just means we start with an n-dimensional space of all real numbers. There's no constraints on x1 and xn. They could be any number. And when you're done, you end up with a real number. So you could think of this function, if you wanted to get fancy, as a mathematical mapping from a 9-dimensional space onto a 1-dimensional space. Or you can just say it's a function, like if you're like me and you think of functions as like block diagrams, it's got 9 inputs and 1 output. That's the idea. Right? So great, we have this function. I haven't talked about what it is at all yet. Let's take its derivative. So when we're taking derivatives of vectors, we have to be very careful to maintain the right shape, size, orientation of the vectors and matrices that we get out of it. So a differential of f, which is a scalar, right? If we have f, which is a scalar, then the differential will also be a scalar, is the derivative of f with respect to x times a differential in x. Well, if x is a n by 1 vector, then this needs to be an n by 1 vector. But now, in order for the matrix multiplication to work out, this needs to be 1 by n. Now, we could also write this out a little bit. Say, okay, the differential of f is what? Well, it's the derivative. Now we're going to do, these are partials, right? It's the partial derivative of f with respect to x1 all the way to the partial derivative of f with respect to xn. So you can imagine taking n partial derivatives of this function. But then each of those would be multiplied by a differential of x1, x2, all the way down to a differential of xn. So we can see visually, this is going to be a 1 by n row vector. This is going to be an n by 1 column vector. Or if we multiply this out, it's going to be differential of f dx1 plus differential of f dxn. Okay, the key takeaway here is the derivative of a scalar with respect to a n by 1 vector, column vector. Let me erase that. Is a 1 by n row vector. So this bit right here is the derivative, which is the same as this vector right there. Okay. As we go through, I realize right now we're just writing down symbols. We're going to do this with actual equations later, and it's going to make a little bit more sense. But questions up to this point, derivative of a scalar is a vector. So far, so good. All right, on to the next one. Next, suppose that in my notes I use H. I'm going to use G actually. Suppose G is a m×1 column vector whose elements are functions of a n×1 column vector X. Okay. So the way we would write that is that G is G1 of x1 to xn all the way down to Gm of x1 to xn. Okay. So we have the first function and then the second function all the way down to the mth function of x, where x is a vector from 1 to n. Okay, so G is just a column vector. Well, now we'll do the same trick. So what is differential of G is going to still need to be, so this is m×1, this is going to need to be m×1. Well, that's going to be the derivative of G with respect to x. And this is going to be multiplied by differential of x, which is an n×1. So, and maybe this makes sense, the derivative of a vector with respect to another vector, we're going to need to go up into 2 dimensions. It's going to need to be a matrix to properly describe this. So this is actually going to be an m×n matrix, Mike by November matrix. Or, we wanted to write this out, it would be the differential of G1 with respect to x1, and then eventually the differential of G1 with respect to xn, differential of Gm with respect to x1, and differential of Gm with respect to xn. So you're going to get this m×n matrix, and then this multiplies dx1 all the way to dxn. So the derivative of a m×1 vector with respect to a n×1 vector is a m×n matrix. Okay, so derivative of a vector, derivative of a scalar with respect to a vector is a vector. Derivative of a vector with respect to another vector is a matrix. Okay, hopefully that all makes sense. Now, I'm going to change gears a little bit. And pretty much the rest of the lecture is going to be more and more intricate examples to try to make this all make sense. And we're going to start to see this in the context of things that we would actually use in this class. But questions up to this point? Okay, don't keep on cruising. Next, let's apply these concepts to some common vector operations. And this is where I'm going to introduce this kind of like split screen effect here, where I want to make vector calculus make sense by reviewing scalar calculus. So for the next couple of examples, the left slide, or the left-hand side is going to be vector land. This is going to be scalar land. Okay, let's suppose we have some function y, which is a scalar, And this is equal to the dot product of some vector A with some vector X. Okay. And maybe in this case, X is like the input and A is like a just a bunch of numbers, basically, a bunch of parameters. So in scalar land, this might look like Y is equal to AX. Okay, great. Now, really quick, somebody key in their mic. What is dy dx in scalar land?
Just A.
It's just A, right? Now, if you want to hazard a guess, and there's no stupid answer because I haven't taught you this stuff yet, do you want to just take a wild guess what this derivative is going to be?
H transpose?
Yeah, it's going to be A transpose. Yep, we just dropped the X. In much the same way that you drop the X in scalar land, you drop the X in vector land. Now I'm going to go through and prove why that's the case, but I'm trying to use the scalar example to hopefully kind of build some intuition. So very good job, thank you. Okay, the way we would think of this is Y plus some differential element of Y is equal to A transpose X plus some differential element of X, right? But now we could split this up, or we could distribute and say Y plus dy is A transpose X plus A transpose differential element of X. And now we're at this point where we have a Y and an A transpose X. Well, those are equal to one another, right? So we get dy is A transpose dx, or dy dx is A transpose. Now, let's see if this passes our gut check, right? Y is a scalar. The derivative of a scalar with respect to a vector, in this case, should be a row vector. And if A is a column vector to start, then A transpose is a row vector. So this should pass the sniff check. All right, so what that means is, more generally, and I'll write this out here, just drop the X, or in this case, I'll say the trailing X. Note that X must be on the right to drop. So this does not work quite as well if we had said, well, okay, if we had said Y is equal to X transpose A, then you can't say that the derivative of Y with respect to X is what? A or transpose A? It doesn't really work. But remember that X transpose A is the same thing as A transpose X. So we'll often use some kind of intermediate tricks to get the thing that we're trying to drop on the right, and then we just drop it like a bad habit. That's the idea. Let's see another example. Hopefully that make some more sense. So now for a matrix example. Yes. So once again, we're going to divide, and we'll talk about vector land and scalar land. So our example now, Y is a vector, and it's equal to some matrix A times X. Okay. Now in scalar land, we kind of have the same example from before, right? So this would be Y is equal to AX, dy dx is equal to A. So does someone want to hazard a guess what the derivative of Y with respect to X is in this matrix example?
Is it just going to be capital A again?
Yeah, probably, right? Because in this case, we know that the derivative of a vector with respect to another vector is a matrix. So yeah, and we learned the just drop X rule. That should probably apply here too, right? So let's take a look. We could go through and prove it to ourselves. Y plus some differential element of Y is equal to AX plus some differential element of X. This is going to look real familiar. Y plus dy is AX plus A dx, cancel, cancel. dy is equal to a dx, or dy dx is equal to a, which is a matrix. So that passes the sniff test there as well. Okie doke. Let's get a little trickier. And after these three examples, we'll actually have most of the tools that we need to kind of survive and thrive in this class. And we'll do some kind of more concrete examples. So here we have vector land, scalar land. Okay, now we're going to say y, we're back to a scalar. Yes, sorry, I just caught a mistake in my notes. All right. Apologies for the dead air time. Just want to make a note to future self so I don't make a mistake. Y is a scalar, and it's equal to x transpose AX. So those of us that have done linear algebra, you're probably familiar with taking a matrix and kind of sandwiching it with a vector on either side. In scalar land, this would be kind of like saying y is equal to ax squared. So in scalar land, the derivative of ax squared is 2ax. So based on that, there's probably going to be some relationship over here where this looks like maybe 2ax, but then we learned we dropped the thing on the right, so maybe it's like 2x transpose A. It's going to be similar to that. We'll see in a moment here. So y plus some differential element of y is equal to x transpose plus some differential element of x transpose A x plus some differential element of x. And if we go through and distribute this out, we get y plus dy is equal to x transpose ax plus differential element of x transpose ax plus x transpose a differential element of x plus differential x transpose a differential x. Okay. Now in this case, we can cancel out y and x transpose ax because we know that they're equal to each other. And also in this case, we've got a differential element squared, so this is approximately 0. So we're going to ignore that. What we get then is dy is dx transpose ax plus x transpose a dx. Okay, now this is a scalar plus a scalar. Remember that when you have something like A transpose B, that's the same thing as B transpose A. And if you have A transpose capital B C, that's the same thing as C transpose B transpose A, right? Well, these are just simple matrix multiplication rules. So we're gonna play a little transpose game here. This is really X transpose A transpose dx plus X transpose A dx, or dy dx is X transpose A transpose plus A. Which might look a little weird, but it kind of looks like 2ax if you blink. If you kind of just like, okay, you've got A plus itself transposed, kind of similar to 2a, and then we've got the x over here. So that's kind of the parallel that I want to draw. Hopefully that makes some sense. And as another check, remember that the derivative of a scalar y with respect to a vector ought to be a row vector. Well, x transpose times A transpose plus A, all of this is a row vector. So that passes the smell check. Right, good stuff. Questions on those last three examples that we went through? All right. Next, I'm going to go through three more examples, but these are each going to be a little bit more involved. I'm going to do the first one, and then the second one I'm going to give to y'all to do as kind of an in-class exercise, see how far you get. And then we'll do the third one, and then we'll wrap up. So now for a more practical example. The Jacobian, some of you might have learned this term in robotics perhaps. It's basically a sensitivity matrix or a sensitivity vector. It tells you about the relationship between perturbations in an input and perturbations in an output, right? So the Jacobian gives insight into how a perturbation in an input like X affects an output like Y. So suppose an object in space, or you could just say an object in general, has position R, and that's going to be some R1, some R2, and some R3 in some reference frame. We're not really talking about reference frames right now. And this is a column vector, so it's really R1 and then R2 and then R3. Okay. The range to this object is the norm of its position vector. So I'm going to call this rho is equal to the norm of R. All right. The Jacobian, and this would be the derivative of rho with respect to R, tells us how changing R affects rho. So you might say, if we'll just do a 2D case, for example, here. If you've got some vector that looks like this, so it's got some X component, some Y component, and you increase its value just a little bit in Y, it's going to have about the same length as it did before, right? Because it's going to be like kind of the, whenever you have a very slender right triangle, the hypotenuse and the long leg look about the same. So changing in Y doesn't really change rho that much, but changing in X, you're basically just stretching it out directly. So if the vector R is almost entirely along the X direction, then rho would be more sensitive to changes in X than changes in Y. That's kind of the idea. Now, none of this really matters for taking the derivative. I just wanted to give you a physical sense of what we're doing here. What I'm saying is find the derivative of rho with respect to R. Go figure it out. So let's do a quick gut check here. A differential element of rho is a scalar, so this is 1 by 1, is going to be the derivative of rho with respect to R times a differential element in R, which is 3 by 1. So this ought to be a 1 by 3. So we know before we do anything else that this should be a rho vector. All right. So here is the pro tip, which is going to make matrix vector calculus doable in this class, because I have no idea how to do the derivative of the norm of a vector. Like, I didn't learn that in calculus class, how to do derivatives of norms. So here is the pro tip, and this is so important, I'm going to write it in orange. Rewrite your vector expression in a way that facilitates the chain rule. And then in parentheses, all exponents and multiplication. That is going to save you so much heartache. So we know that rho is the norm of R, but what does it mean to take the norm of R? Well, if you take a vector and then take the dot product of that vector with itself, and then take the square root of that result, that is the same thing as taking the norm, right? So R dot R square root, or you could think of it as R transpose R to the 1/2 power. Now, all of a sudden, we have a hope of being able to take the derivative. Okay? Because we can use derivative rules that we learned in high school. So derivative of rho with respect to R, and pardon me, I caught myself making a mistake in my notes again here. There we go. Is what? Well, whenever we take the derivative of something in scalar land, we would move the exponent to the front, we leave the interior of the parentheses, and then we multiply that by the derivative of whatever's in the interior, right? And then we have to subtract 1 from the exponent. So following the chain rule, this should be 1/2 R transpose R to the negative 1/2 power multiplied by whatever is the derivative of R transpose R. Okay, so let's do a quick aside. Okay. If Y is R transpose R, then you could think of it as dy, or actually, before we even get there, because we haven't learned how to do the derivative of two vectors being multiplied, but you could just as easily say that Y is R transpose identity matrix R. And we do know how to do this. The derivative of Y with respect to R would end up being R transpose identity matrix transpose plus identity matrix, which is just the same thing as 2R transpose. Okay. So hopefully that makes sense. The derivative of x squared is 2x. The derivative of R transpose R is 2R transpose. Shouldn't be a shocker. So if we plug that in, we get the derivative of rho with respect to R is 1/2 R transpose R to the negative 1/2 times 2R transpose. Cancel, cancel. We're almost done. Isn't R transpose R to the 1/2 power just rho again? Like, I'd rather not state this as my final answer because it's a little bit messy. I'm going to simplify things just a little bit. The derivative of rho with respect to R is just rho to the negative 1 power, right? Because we know that rho is R transpose R 1/2. So R transpose R negative 1/2 is just 1 over rho R transpose. So the sensitivity of rho to changes in R is 1 over rho R transpose, and this would be our final answer. And bonus, it's a row vector. Sorry, I keep saying row. There's this row and then there's this row. I realize I'm throwing both of those around. This is a ROW vector, right? Because it's a 1 by 3. So, example vanquished. Any questions on that? Was that followable, hopefully? All right, I hope so, because the next one you're on your own. So I'm going to set up a matrix vector calculus problem, and then I'm going to give you maybe 10 minutes to try it on your own. Ordinarily, I know I try to give you a 10-minute break during these lectures, but this lecture is probably going to be pretty short. So we're not going to do the 10-minute break. We're going to do a 10-minute practice problem, and then we'll just burn through the rest of it. So I'm going to set it up, and then I'll just shut up for 10 minutes. We'll see how far you can get. So now try this on your own. two-body motion linearized about a reference trajectory. And this will absolutely come up in this class. So first of all, remember that the two-body equations of motion, r double dot is equal to negative mu over the norm of r cubed. R is super nonlinear. Okay? So here's what I'm into. We're going to say we will define the translational state of a spacecraft as x, which is defined as position and velocity. And we've kind of already seen that in homework 1, right? If you have the position and the velocity of a spacecraft, you can propagate that forward, either using Kepler's equation or two-body, that sort of thing. Two-body equations of motion and then a differential solver. So this is RV. So then the derivative of the state is going to be velocity acceleration. Or you can think of it as R dot and R double dot if you prefer. We seek the 6x6 matrix. So I'm kind of cheating. I'm telling you what size the answer is going to be. We want the derivative of the state with respect to the state. So we want dx dot dx, which can be split up into 4 submatrices. This is really the derivative of velocity with respect to position, and then it's the derivative of velocity with respect to velocity. And then it's the derivative of acceleration with respect to position. And then it's the derivative of acceleration with respect to velocity. So we need all 4 of these sub-matrices. You figure each of these is going to be a 3x3, so that when you stack them together, you get a 6x6. So it is 2:38 for you. Let's discuss at 2:50 Eastern time. See how far you can get. All right, so we're a little bit halfway through the work time. Just wanted to give you a little hint in your consideration here. 3 of these sub matrices are going to be trivial, right? So for example, derivative of velocity with respect to velocity is just itself, right? So in matrix vector land, that would be the identity matrix 3 by 3. Only one of these 4 submatrices is going to give you any serious problems. So hope that helps. All right, so by my count, that's 250. So let's talk about what we did. So I'll go through and show my work, but I wonder if anybody can key in their mic and tell me which one of these 4 is a bummer, and then which are the 3 easy ones.
I want to say DADV is the bummer.
DADV. I actually had a different one that was giving me trouble, but let me show you what I'm thinking about here. Oops, we got some stray marks here. Okay, let me. So first of all, velocity. We don't really have velocity as a function of position because velocity isn't a function of position, right? You can have some position and have any velocity according to the two-body laws of motion. There isn't a velocity equation. So we could just say the derivative of velocity with respect to position is nothing. There's no r in the velocity equation. Similarly, the derivative of velocity with respect to velocity is itself, right? Derivative of x with respect to x is just 1. Well, in vector land, it would be the identity matrix. Now, similarly, we don't, for acceleration, this is our acceleration equation right here, r double dot. And you'll notice that velocity does not feature in r double dot. So actually, derivative of acceleration with respect to velocity is 0. But the other one is a bit of a problem. So the derivative of acceleration with respect to position, well, that's the same thing as the derivative of r double dot with respect to r, which is derivative with respect to r of negative mu over r norm cubed r. This is the ugly one. This is the one that we're going to have to use the techniques that we've learned in this lecture. Okay, well, let's think about it. What is the golden rule of matrix vector calculus? Rewrite your expression in a way that facilitates the chain rule. I don't know how to do the derivative of a norm cubed. That's scary to me. But what I can say is that this equals derivative with respect to r of negative mu, and then we've got r transpose r to, okay, we have to be careful here. So rho is the square root of r transpose r, right? Which is the same thing as r transpose r to the 1/2. Okay. Similarly, 1 over rho would be r transpose r to the negative 1/2. So what we're looking at is 1 over rho cubed, which is r transpose r to the negative 3 over 2. Okay, so that's why I'm about to put a negative 3 over 2 as our exponent here. Hopefully that makes sense. So this is to the negative 3/2 power, right? And then this is multiplied by r. Right? So this and this are the same expression written 2 different ways, but this one I actually know how to do the chain rule to. So hopefully not quite as scary. Okay, so the derivative of a with respect to r is equal to, okay, so this is where we have to use the multiplicative rule and the chain rule together. So it's going to be the first bit times the derivative of the second bit plus the second bit times the derivative of the first bit. Remember that? Or 1d2 plus 2d1 might be how your teacher said it. That's how my teacher said it. So let's start by taking the derivative of the first bit. This would be 3, so negative 3/2 times negative mu is going to be 3 mu over 2. And then the interior is unchanged, right? It's still r transpose r, but now it's to the negative 5/2 power. Okay. And then we've got the derivative of the interior. So the derivative of r transpose r is 2r transpose, but that actually goes on the end. And we'll see why in a minute. The matrix dimensions won't work unless we do it this way. And really quick, before we even move on, this 2 cancels with this 2. Okay. Now, all of that is the derivative of the first times the second. So that's 2d1 in this case. We still need to do 1d2. So that would be minus mu r transpose r to the negative 3/2. And then the derivative of r with respect to r is the identity matrix. 3 by 3 identity matrix. Okay, let's clean this up a little bit. The derivative of a with respect to r is equal to what? Well, it's going to be 3 mu divided by r transpose r square root, so that's rho in this case, to the 5th. So I'm going to write this like this. It's 3 mu over norm of r to the 5th r transpose minus mu over norm of r cubed identity matrix. And we're just going to call this G for now. All of this. Now, this should make sense. Notice if we had done R transpose R, this term would be a scalar, but it's important that this term be a matrix, right? The derivative of a vector with respect to a vector is a matrix. So this is going to give us a 3 by 3 minus a 3 by 3. That's still going to be a 3 by 3. Okay. And so to answer our question, the derivative of the state with respect to the state, or the derivative of state dot with respect to state, is 0 identity. This ugly mess, which we're going to call G because I don't want to write it all out again, and then 0. And we will absolutely have an example coming up later in this class, several lectures from now, where we do this exact exercise, the derivative of position velocity with respect to, or sorry, derivative of velocity and acceleration with respect to position and velocity. And I'm just going to go, oh, remember lecture 9? Copy paste those results. So hopefully that all tracks. Any major questions on this example? All right, cool. We've got one more example and then we're out of here. This one will probably take about maybe 10-ish minutes. So it should be a short lecture. Right. Our final example, I want to introduce another topic which we're going to use in concert with matrix vector calculus, which is optimization, which is something that we're not really going to go over a ton in this class. There's really one trick from optimization that we're going to need, but I definitely highly recommend that any of you who have the opportunity go take numerical design optimization with Dr. Jason Hicken at RBI. He's really good. Taught me a lot. So our final example borrows concepts from design optimization. So returning briefly to scalar land. Let's say we want to find the minimum of some cost function j of x is equal to x squared. So a lot of design optimization is setting up really fancy equations. So x squared is not a fancy equation, but it's definitely going to get the job done. Finding a really fancy equation which describes something that you don't want. So we call that a cost function. And then what we do is we find the input that minimizes that cost function. Now you could also create a function of something that you do want, call it a reward function, and then try to maximize that. It's the same math problem up to a minus sign, right? Same idea. So you're finding the minimum of this function. Now, those of us that know what this graph is, this is going to be a parabola, right? So we know that what we're about to do, here's x, here's j of x. This is a parabola, which just touches the origin. Okay, so we know that this is the answer. The minimum value of x is 0 because 0 squared is 0. Any deviation from that, and you're going to get some non-zero cost. So obviously we know the solution is x optimum. So when you use an asterisk as your in the place of an exponent, that means optimum. So the optimum x value is 0 because that gives us the lowest possible j value, right? The technique that we will use is more complex, but we'll see it gives us the same answer. So the technique we use borrows from calculus. Let's say that we had a function that was really gory looking and you knew that it would be a pain to graph it and it would be a pain to think it through. But we also know that the minimum value is going to be the point where the derivative equals 0. So if you remember from calculus class, right? If you're trying to find local maximum and local minimum, you set the derivative equal to 0, same concept. So maybe this is like a really weird and lumpy, I don't know, maybe we'll do something else. Let's say that the cost function does this, and then like, I don't know, maybe it bottoms out here, and then it does some other wiggly stuff up there, right? We know that this point right here, where the derivative equals 0, is the bottom of the valley. And so even if your cost function is really ugly looking, the basic premise, set the derivative equal to 0, is still going to work for you. So we take the derivative of the cost function. We set it equal to 0, and we solve. So even those of you that haven't taken design optimization, now design optimization covers quite a bit more than this, but you would be amazed how far you can get by setting up a cost function, taking a derivative, setting it equal to 0. We're going to do it a lot in this class. So the derivative of j of x with respect to x, okay, well, j of x is x squared. Derivative of that is 2x. Okay, so if 2x equals 0, then x equals 0, or our x optimum equals 0. Right? Not too painful. Let's return to vectors and matrices. And use this technique to solve an over-constrained linear set of equations. Okay. So let's say we have A, x equals B. Matrix times vector equals vector. And I say, given A and B, find x. And you might say, that's easy. X is A inverse B. It's like, okay, yeah, some of the time, in some examples. In other examples, you can't invert A. It's not quite so simple, right? If A is a matrix that is longer than it is wide, which means that there are more equations than unknowns, we end up with a problem that we're going to talk about, I think in the next lecture, if not in the next lecture, then very soon, where you have only, let's say x is an n by 1, and a is maybe an n by n. You only have n numbers to play around with to solve m equations where n is greater than n. So there's actually no way to make ax equals b. Instead, what you try to do is make ax minus b as small as possible, right? And you can think of it as if you take the sum of the squared error and minimize that, then you are finding the least squared error. This is the least squares techniques of solving equations. And we're going to go into much more detail on least squares very soon. But for now, we will set up a cost function. Which looks like this. J is 1/2 norm of ax minus b squared. So that is to say, ax minus b is going to be some error vector. Take the norm of that error vector squared 1/2. That is our cost. Okay. Now, remember our golden rule of matrix vector calculus. We're about to take the derivative of j. So here we are. This is the big time. We're taking the derivative of a vector and matrix set of equations. We're going to rewrite this as 1/2 ax minus b transpose ax minus b. Right? Because remember, the norm is ax minus b transpose ax minus b quantity square root, but it's squared, so that cancels itself out. So this is our cost function that we're trying to minimize. So we set the derivative equal to 0. So what is dj dx? Well, let's think about this for a second. dj dx, j is a scalar, right? We've got a vector transposed with a vector that collapses to a scalar, 1/2 still a scalar. Derivative of j with respect to x ought to be a vector. Okay, but let's actually go through the whole procedure. It's going to be, remember, it's the derivative of the first times the second plus the derivative of the second times the first. In this case, we're going to say it is 1/2 ax minus b transpose, and then what's the derivative of ax minus b with respect to x? B cancels, and the derivative of ax is just a, right? We already learned about that. Plus 1/2, and this is going to be a transpose ax minus b. Hopefully you see the symmetry here. Right? Now, if we go through and distribute, this is equal to negative 1/2 b transpose a plus 1/2 x transpose a transpose a plus 1/2 a transpose ax minus 1/2 a transpose b. Right, all we're doing is distributing. And if we gather like terms, this, which by the way is equal to 0, is going to be a transpose ax minus a transpose b. And if that's equal to 0, then after one more step, we can say that x optimum is a transpose a quantity inverse a transpose b, which is the least squares solution. Some of you might even have this memorized. This is where it comes from. A transpose A inverse A transpose B is the solution in the least squares sense to AX equals B. And we did that by using matrix vector calculus and design optimization techniques. And this will absolutely come up again because we're about to do this same type of thing, but for more and more complicated equations. I think if I remember correctly from last year, this type of thing is going to come up chiefly when we talk about estimation theory. And then also when we get to sequential estimation and Kalman filters, there's going to be a lot of partials there as well. So then this, I believe this also comes up on homework too. Anyway, questions on this example or just matrix vector calculus in general? Otherwise, that's about it. All right, I'm going to go ahead and stop the recording, but I'm going to stick around for either homework help or just chit chat. But yeah, thanks everybody for coming today, and I'll get this recording up as soon as I can.